All right, thanks a lot. Can you all hear me?
Yes.
Everything's good? All right, great. So today I want to talk about a perspective on how to use machine learning in conjunction with robotics. So this talk will be focused on specifically using tools from online learning to develop adaptive robotic systems. So I want to start by thinking about how to design intelligent robots. And I think there are basically three completely different ways of thinking about this problem. So on the left here, what I've labeled as models is basically automation. So this is classical robotics, which includes things like modeling, simulation, mechanics, and controls. And it relies heavily on prior knowledge of the system as well as the task environment engineering. So these methods are very efficient in terms of compute, but brittle in the face of changing properties of the robot or the environment. On the right, we have a completely different approach to trying to design intelligent robotic systems, and that's basically using machine learning. So more specifically in the context of this talk, by learning, I mean model-free reinforcement learning. And the idea here is that we can learn how to behave directly through the robot's interaction with the environment. And this works really well for generating behavior where it's not easy to write down a model a priori. Now, unfortunately, this can also be really expensive in terms of data and compute compared with model-based approaches and automation. And then finally, at the top of the triangle, we have an important area of robotics that I think is often overlooked by those of us who are really focused on AI research, and this is teleoperated robots. So many of our most successful robotic systems, like the Da Vinci surgical robot, PackBot, and many types of drones, have extremely capable hardware, but rely on human expertise for decision-making. So in summary, these are different ways of approaching robotic intelligence using models, planning, and control, or machine learning, or designing capable teleoperated systems. But they're often viewed as being at odds with each other. But for me and for my lab, we kind of think of all of the interesting questions as actually lying in this area, sort of in the center of the triangle, where these ideas converge. And we're already familiar with some of these intersections, such as adaptive control, imitation learning, and human-in-the-loop models. Okay, so today I really want to focus on three different approaches to designing robot behavior and how they can be related through online learning. So we'll talk about model predictive control, reinforcement learning, and imitation learning. And along the way, we'll discuss how reasoning and prior knowledge can be combined with data for designing more effective robotic systems. But first, I want to just give a very, very brief background about online learning, which is a sub-area of machine learning, and why I think that it's particularly relevant for robotics problems. So let's start by thinking abstractly about what a robot is. So here's my idea of a robot. So usually we can assume that the robot can perceive the environment and take an action which changes its relation to the environment somehow. So this is the basic robotic paradigm. But for robotics, or for robots that adapt their behavior with experience, we often need to break this down a little bit further. So we usually call the function that takes states or observations as input and produces actions as output a policy. And the policy itself has parameters, which are represented by theta here. And if the parameters stay the same, then the robot's behavior stays the same. But if we want robots which can learn from their mistakes, whoops, let me try to go back. We've managed to go, whoa, really far out of the way. Sorry. So if we want robots which can learn from their mistakes and handle more complicated environments, we can specify a learner that updates the policy parameters to improve at some task with experience. And so we've entered the learner now here into the robotic framework. The task objective function, which is J here, tells us how good the policy is and guides the learner. Okay, so this is one way of thinking about adaptive robotic systems, where what we've done is we've really highlighted the robot's relationship to the environment. But alternatively, we can focus on the learner. And here, the learner can be viewed as interacting with a complex system consisting of the robot in its environment. we can think about this setup as actually online learning. So in online learning, at every round of learning, the learner plays some decision. So in this case, the learner is choosing some parameters for the policy or defining a policy that then gets played in the environment. And I can think about deploying the policy in the environment and evaluating how well it performs as kind of an adversary, which is selecting some loss function for me. Then the learner is going to use that loss in order to update its decision or update its parameters for the next round and hopefully improve at the task. So why does this framework make sense for robotics? So let's step back and think carefully about how robots should learn. Now, empirical risk minimization is the dominant paradigm for thinking about machine learning algorithms, and it's used to guide how we should think about basic problems like classification and regression. But I think it doesn't really make a lot of sense for robotics. So first, robotics data is not IID. Robots collect data which evolves over time, and they interact in closed loop with their environment. Second, analysis like statistical consistency doesn't really make very much sense for robotics. So generally, the models that we try to learn in robotics problems are necessarily approximate, and the data generating process typically does not live in the model class that we're trying to fit. So we need the appropriate type of theory for the learning problems that we're encountering. And then finally, data is not batch, but it's streaming in robotics problems, right? So it's collected through a robot's interaction with the environment. So unlike empirical risk minimization, online learning makes very minimal assumptions. It mainly focuses on the concept of regret minimization. So for stationary policies, and what I mean by that is a policy that works everywhere in the environment, minimizing regret means learning a sequence of policies that compares well with the best policy in my policy class in hindsight. So in other words, I want to learn very rapidly. I want to do the best that I can given my policy class and the data that I've seen so far. There's also this notion of a non-stationary policy where basically I want to learn the best policy for a particular state in my environment. And for non-stationary policies, what I really want to do is learn a policy sequence that is performing as well as possible with respect to the best sequence of policies that I could have executed. And this is much harder to minimize. So online learning focuses on notions of regret like these. But online learning is also very general in that it does not make the IID assumption. And online learning is agnostic with respect to the ideal system. So I'm just trying to learn the best policy in my policy class. So just in summary, we can think about online learning as a perspective which will enable us to unify various algorithms which we may have seen in reinforcement learning and model predictive control and other areas. It explains empirical performance well, so we can often bound the performance that we actually see in practice using theory derived from online learning. And it suggests new approaches. It provides a framework for developing new algorithms which we expect to work well in practice on real systems. Okay, so let's see how we can use online learning to solve really interesting robotics problems. So to motivate this talk, here is one of our robots. It's a high-speed off-road ground vehicle built in collaboration with several labs in computing and aerospace engineering at Georgia Tech. And the goal is to autonomously race this vehicle faster than a human can pilot it on terrain like dirt tracks. So just to tell you a little bit more about the platform, it's a 1/5 scale vehicle. So it's about 1 meter long. It weighs about 45 pounds. It has electric motors which allow it to race at about 100 kilometers per hour. It also has cameras, IMU, GPS, wheel speed sensors, so sort of a full sensor suite on board, and then considerable onboard computational resources, an i7 processor and a GPU. And we do all of our computation on board the vehicle while it's racing at high speed. We can control the vehicle by steering and modulating speed with throttle commands. And then we have this sort of goal, right? We want to try to drive this thing as fast as possible. And we can think about this as kind of an AI problem where we want to find some policy which maps our sensor data to our motor commands or to our simple actions so that the car races at high speeds over rough terrain without crashing. So how do you do this? And maybe why is this a difficult problem? So I'm about to show you a slow motion video of the dynamics of our car as it's taking a turn at high speeds. I'm not sure how well the video will come through here on Zoom, but we'll give it a shot. And what you'll see here with the car, let me explain what's happening, is the car is bouncing and sliding. And it's behavior which is very difficult to predict and virtually impossible to simulate accurately from first principles. And if you don't get this right, it can cause a number of problems and actually cause the vehicle to crash when we're trying to pilot it. So what we're going to do is we're going to think of trying to find a policy to control the vehicle as online learning. And in this case, the learner is going to be tasked with choosing a good sequence of policy parameters that will be evaluated by the robot and its interaction with the real world. So we're going to try to solve this problem of controlling the vehicle in several different ways, but I want to start by showing you how we can do this with model predictive control and then how to think about model predictive control as online learning. So despite what my machine learning colleagues may tell you, classical engineering is actually a very good starting point for finding a policy in a high-speed ground vehicle like this. To start, we decompose the problem into these individual unit-tested components where we take our sensor data, we perform some sort of perception on that data. We turn this into a state estimate. So in this case, we're going to use differential GPS and IMU to get accurate outdoor position to within a few centimeters. Then we're going to localize the robot with respect to a map, and we're going to do this at high speeds, about 200 hertz. And finally, we'll assume some system model and use model predictive control in order to actually generate the actions for our vehicle. So this is our overall pipeline. And for those of you who aren't familiar, the way that we think about model predictive control is that it's just a very pragmatic way of designing a policy. It doesn't attempt to build a single complex policy that works well everywhere in the environment, but uses a very simple policy class and re-optimizes this aggressively at states that we encounter. So this is kind of the way that we think about this. Now, the interesting thing is that we can view model predictive control as online learning, and this gives us some insight into model predictive control algorithms and prescribes a way to generate new algorithms. So in order to see this, I'm just going to kind of show you how we've developed a model predictive control algorithm that kind of accords with online learning. So on the left, we have our online learning paradigm, and on the right, we're going to specify choices for this particular high-speed racing problem. So first, each round of online learning will correspond to a time step in the system. That is, the learner will pick a new policy at every single time step. And then second, the policy will just be a simple open loop control distribution. We can think about this as a distribution of trajectories of actions. Now note that this policy is not conditioned on state. It's literally just a distribution of action sequences. Okay. So next, given a model of the dynamics, we're going to run our open loop controls and simulate the state action distribution. And the objective is going to be the expected cost under this distribution starting from the current state ST that we are tracking in our environment. And in our application, our cost terms will include terms like stay near the center of the track, drive as fast as possible, minimize acceleration. So basically, by generating a state, we can actually view the environment as our adversary, which is picking out a loss function to evaluate our policy on. So essentially what we're saying is we have this open loop control distribution, we pick this, and then the environment says, I'm going to put you here in your simulated world. Now you're going to obtain some loss based on your objective function in simulation. So this is kind of a slightly different way of thinking about things, but you can actually view this now as an adversary selecting a loss function at every round as the robot is moving through the environment. So then from the online learning perspective, we want to update the parameters of our policy based on our loss. So our goal is going to be to minimize dynamic regret, although it's going to be difficult to prove anything about this in this particular domain. So to accomplish this, we're going to use an algorithm called dynamic mirror descent, which basically has two steps. So in the first step, it performs mirror descent to update the control distribution so that it has lower loss on our objective. In other words, so that it performs better in simulation. And then mirror descent is going to build a convex global upward bound approximation of the objective using a gradient G, a step size lambda, and a Bregman divergence. And you can think about the Bregman divergence as just a general class of divergences, which includes things like squared distance and KL divergence. It then minimizes this surrogate objective function. The result is going to then be an updated control distribution that performs better in the simulator for the current state ST. And then we're going to execute the first action from the updated control distribution. And then the second step of dynamic mirror descent is the dynamic part, which uses a predictive model to shift the distribution forward a time step to time step t+1. And you can think about this as sort of analogous to a state space model in a Kalman filter. The online learning algorithm then moves to the next round, which uses the open loop control distribution together with the next state. Now, the interesting thing is, this is a very general optimization framework, right, which is using mirror descent in order to choose how to update this policy, which is informing our actions at every time step. And the interesting thing about this is that it provides a framework which unites a very large range of different model predictive control algorithms. So you can actually develop very simple, clean derivations of MPC algorithms with special cases of this approach. You just choose a policy, pick an objective to optimize with dynamic mirror descent. And we're basically leveraging this powerful optimization tool in order to kind of see what these details are and to think about how these methods relate to each other. Now, an interesting thing about this is that this perspective suggests that actually many of the off-the-shelf MPC algorithms are actually suboptimal and make a number of heuristic choices that are unjustified in the broader perspective. And so this allows us to potentially develop better algorithms or fix previous approaches by doing things like modifying step size, which is really important for optimization. This also provides a prescriptive approach to model predictive control design. So we can easily generate new algorithms that make sense for a particular application. An example of this are like the exponential family of control algorithms down in the lower right-hand corner of the screen, where we can develop new specific cases of MPC with different distributions and different divergences. So for our task, we're going to use variations on MPPI. We're actually going to relax the distributional assumptions and tune the step size, which is okay in our framework. And you know what I just want to kind of throw up here. Here's a few publications which are related to this. So if you're interested in learning more about the actual approach, you can see some of these recent papers. And here are some results. So basically, what you're seeing is that we can use an algorithm like this to race our car at speeds which are faster than any of our grad students can pilot it around the track. And it's able to do this about a second faster, so about 10% faster than a human pilot. And you can see that it's a very responsive, robust algorithm. Okay, so next I want to kind of move to the RL part of the talk, and we can see that a lot of the tools that we'll use are actually interestingly similar to the tools that we used in the first part. Here we're interested in end-to-end visual navigation. So we're going to try to map images and from a camera and noisy wheel speed sensors directly to steering angle and throttle commands. And the idea here is we want to find a policy that controls the car at high speeds over rough terrain without crashing. So we're going to parameterize a policy as a deep neural network. And now we have to think about how do we train a network like this in this real world system where driving fast is dangerous. So first, let's think about what kind of problem this is. So at its essence, this is basically a reinforcement learning problem. And here the goal is to directly find a policy parameterized by theta that maps states or maybe observations to actions. Our objective seeks to find an optimal set of parameters that minimizes accumulated cost. We want to note a couple things here. So first, that the expectation is taken with respect to the distribution of states and actions induced by the policy that we want to learn. So this is a fairly difficult optimization problem. And the cost terms here are instantaneous cost, which in our case basically says that driving slowly is bad, crashing is bad, and lots of actuation is bad. Now, I'm going to try to cover this very quickly, but we can also view training this deep neural network via RL as an online learning problem. So every round or iteration here is now an episode. So in other words, we make a decision, that is, we choose a policy, we run the policy in the system for some amount of time. And here the policy is basically the deep neural network itself. It's stationary, so we'll use the same policy everywhere in our environment. And the per round loss is the accumulated cost that the policy incurs over the episode. So our goal is to minimize static regret here. That is, we want our policy to converge quickly to the best policy in our policy class. And this can be hard to optimize because of this per round loss, typically non-convex. So again, we're going to use mirror descent as our tool of choice. Now, with this kind of online learning perspective, using mirror descent actually defines an entire family of familiar policy gradient algorithms, where different choices of the Bregman divergence results in different algorithms. And it is super interesting because all of these popular algorithms that you see on the left here basically only differ in the regularization term of mirror descent. And then also maybe how they approximate the gradient with, let's say, Monte Carlo or advantage estimation. And this potentially explains why, despite all of the fanfare about how various new RL algorithms, can solve problems better than each other, they're actually often pretty similar. And in particular, using a Fisher information metric or negative entropy as the divergence in mirror descent is a good idea, but the specific algorithm may not matter too much in practice. So despite their popularity in reinforcement learning, policy gradient approaches like the ones which I just summarized in the previous slide also have clear limitations. So they're generally subject to noisy and biased gradients due to the challenge of estimating the objective function well, and their updates are myopic. So they're taking these very small steps to a local fixed point in the optimization landscape. And at the end of the day, these issues mean that reinforcement learning agents require a very large number of interactions with the environment in order to succeed. Now, this can actually work for games and simulated tasks, and we've seen this explosion of deep RL papers that use these sorts of environments for evaluation. But with real systems, training is significantly more difficult and data is harder to come by. So we can't run the robot faster than real time, and costs incurred while interacting with the environment are real. So we want to avoid mistakes as much as possible. So this brings us to imitation learning, which is a way to address some of these issues. So basically, we think of imitation learning as a way to accelerate policy learning by leveraging prior information. And the prior information can come in many forms, but we assume that it's encoded in an expert policy. And the main insight here is that expert policies can help us to define surrogate loss functions that are easier to optimize than the original RL loss. So essentially, we're comparing the performance of the policy that we want to optimize to an expert policy, and then we're trying to minimize the performance difference. Now, in practice, we can upper bound the performance difference with a statistical difference, and different divergences lead to different well-known imitation learning algorithms. And if we move the evaluation of the expert policy to the right-hand side of the inequality here, like this, then we can see that we can basically upper bound our objective. Minimizing this upper bound, we see that the first term here is constant, so we can remove it. And this results in a new objective. However, minimizing this objective is still an RL problem. So even though we're trying to match an expert, we haven't actually made our optimization problem easier. So with a small change, we can actually do this. We can minimize a simpler convex function. And the key here is to change the distribution that the expectation is taken with respect to. So here we're fixing it to the distribution of the current policy. And now this loss can easily be convex. So for example, it can be like the L1 or L2 distance between the policy and the expert actions. So going back to our online learning perspective, the per round loss is convex with respect to the expert policy. And keeping everything else in the problem the same, we can get significantly better performance compared with RL. So just as in model predictive control and RL, mirror descent defines an entire family of imitation learning algorithms. So different losses result in different algorithms. Using differences in actions results in dagger, and differences in advantage results in aggravated. And different divergences result in different variations. So for example, we can define all sorts of new algorithms like a TRPO version of aggravated. So now we have a way of overcoming some of the limitations of RL. We can tackle noisy and biased gradients by optimizing these surrogate objective functions, which are more informative. That is, we're going to take big steps towards expert performance instead of bootstrapping over our own performance. And we can attack myopic updates by using the online learning perspective and mirror descent. So when we construct a loss around the global expert, this allows us to develop a learning algorithm with, on average, improvement towards the global optima. And we can actually prove things about the convergence of this type of approach. So the main insight is just that expert policies define surrogate loss functions that are easier to optimize. So I want to just briefly return to the problem of optimizing a deep neural network policy to use vision in order to control our high-speed off-road robot. So here we have our learner, which maps camera images and wheel speeds to steering and throttle commands. And for the expert, we're going to use the MPC algorithm, which I talked about in the earlier part of the talk, which relies on GPS and IMU to estimate state and aggressively update its very simple policy. So this algorithm actually relies on a $12,000 sensor suite. So if we can get a neural network to drive the same way with like a $500 camera and wheel speed sensors, that would be pretty cool. And the last part of the system is our safety controller. So it turns out that we can do this. So what you're seeing here is autonomous driving using these low-cost onboard sensors. And essentially what we've done is we've trained our policy, our deep neural network, to see by mimicking the policy of our MPC expert, which is using high fidelity IMUs and GPS. And one of the things that we see is we're able to achieve almost identical lap times with an MPC expert, even though the conditions on the track can be shifting and lighting conditions can change and things like this. Okay, so just to conclude, we have a number of recent papers on imitation learning. If you'd like to learn more or learn about imitation learning's relationship to reinforcement learning and how it can accelerate things. And just to summarize, there are a few major salient points in the talk. So online learning is a perspective that can serve as a unifying framework. It provides simple derivations, insights from optimization, and the perspective suggests new and better algorithms by really focusing on how to optimize something well. Model predictive control is an effective approach to handling challenges like complex and dynamic environments with very simple models. You can view this as local optimization of simple policies, and it's very effective in practice. Reinforcement learning can learn complex policies and solve extremely difficult problems, and it's state-of-the-art in a number of areas. And the takeaway is that machine learning can work, right? Data is revolutionizing how we attack fundamental problems in all of these different areas. But the key is understanding how to effectively generate data and generate enough data and then leverage the data to build better solutions. And these 2 points are not easy, especially on real-world systems. And then finally, imitation learning is a very general way to accelerate policy learning. So it provides a way to leverage models and simulators and human experience and combine strategies together. And it does this through surrogate objective functions, which are easier to optimize. So I just want to thank a number of grad students who have worked on the work that I've shown here today. These are students at Georgia Tech and University of Washington from a variety of different disciplines, including computing, aerospace engineering, and electrical engineering. And with that, I'll wrap up. So thanks a lot.
Thank you for the great presentation. So I don't see questions in the chat nor in Slack, but I have some question on my. I have some question, but I will just ask one. So I wanted to ask you this: do you think it's easy for your framework to handle also noisy expert demonstrations? Because like in the last scheme, when you have the model and then you're learning from the expert, and your expert is actually the MPC. So in my experience, it frequently happens that if you ask an expert to provide a demonstration, maybe the first demonstration that he provides is not really the optimal one. It takes some time to learn how to interact with the robot, and then maybe he will do it once and two and three. So maybe it will give you some demonstrations that are like noisy. And so how do you integrate this?
Yeah. So basically there's a fundamental problem where your demonstrations may be suboptimal or your expert may be suboptimal. And that suboptimality can come in different forms, right? It can come from noisy demonstrations. It can come from an expert who's actually not able to solve the problem or doesn't know how to solve the problem optimally. And in general, this is difficult because when you're doing imitation learning, generally the guarantees are that you can, like at best, match the performance of the expert. But really what we want to do is use the expert in order to inform how to do policy learning faster, but not be limited by the noisiness or the other sort of suboptimalities which occur in expert performance. So how do you do that? And there's really one simple way which you can use overcomes a number of these issues. Maybe not in every single scenario, but the simple thing is you first do imitation learning using the noisy or suboptimal data, and then you just do a hard switch to reinforcement learning at some point. And the interesting thing is, if you randomize this, if you randomize when you do that switch, you can actually avoid kind of overfitting to that expert demonstration and then start learning. And by randomizing, kind of, using the right distribution, when you do the switch, you can show that you get almost optimal performance, as if you're learning kind of on top of the expert. So if you're just sort of learning over the expert. So this is a really interesting topic and something that we're super interested in just in general and are trying to actually prove theoretical results about.
So because now this is very interesting for me. So so is there like an empirical demonstration that says you have to randomly switch from trying to match the expert and do reinforcement learning to improve? Is there like a formulation?
Actually, well, yeah, so there's theory which will tell you how you should generate the distribution to determine, when you should randomly switch. So you'll kind of like draw from that distribution, and then that helps you determine when to switch. So there's theory behind that. And then you can actually show empirically that that this works extremely effectively. So we have a paper on combining reinforcement learning and imitation learning at UAI from a couple of years ago on exactly this topic, which
maybe
has
if you can if you can write the link, post the link on Slack or on the chat, it would be nice.
Yeah, sure. I'm happy to do that.
Yeah, thanks. By the way, there is a question actually. So it's from Yash Goel, and he asks, the aggressive cars seems like a reactive policy. How do you see it extending it for long-term tasks, or maybe different actions within a task and not just one action?
Yeah, so in general, this also depends on kind of like how you attack this problem. Are you using model predictive control or reinforcement learning? In both cases, though, if you're thinking about sort of trying to solve tasks which require longer range reasoning, usually that has to come into the objective through either a plan, which you might generate in advance, or through something like a value function or approximate value function, which has encoded that information. So there are a number of ways of kind of getting at that. And so, for example, if you want the car to drive like over the course of a mile or something like this, while avoiding obstacles, but also getting to a specific goal, then you need to have this kind of broader understanding of the environment, maybe a map of the environment, and then think about, okay, like what is the global plan or global value function which can kind of pull me in that direction. There's a number of ways of attacking that problem. In the examples that I've shown here, we have some of that information basically baked into the cost function, which is saying like stay kind of close to the center of the track or stay close to a trajectory. And then that's the thing which is being optimized. So there are some design choices which need to be made for a particular problem.
Okay, thanks. So I saw that we have some other questions, but we're running late. If you can answer in the chat for these people, it would be great. Thank you very much. Thank you again.
So one thing I just want to mention really quick is that unfortunately, I'm not going to be able to make the panel later because I'm teaching a class. But I'm happy to answer anyone's questions over email. So just send me an email and I can answer there, or I'll try to get involved in Slack. All right. Thanks a lot, everyone.
Thank you. Okay.